When we've picked our first arrivals from all 7 of the shots within our spread, we get a picture which looks something like this. The green lines show the lines of the first break picks from the previous files. The pinky red file here with the little red ticks on it shows the first arrivals that I've picked from the current shot record. The next processing sequence basically will take the travel time information that underlies where these green lines are and this pink one, and it will transform into what we call a time distance or an XT graph, which is purely a graphical representation of what we see on the screen now. Now, just remember that when we do this, the first screen that we get when we open our file is effectively twisted through 90 degrees. So what is the y-axis on here will become the x-axis in the next graph that we will see. The second portion of our refraction processing, or the inversion portion, we use the module within Seisimager which is called Plot Refre. Now the first thing that we need to do is come to File and open our travel time data. I'm going to open file number 1. As you can see here, it is actually quite a small file, approximately 12 kilobytes. All it is a simple text file which contains information about the distance and time. Select Open, and now the program will take this text file and draw a time distance graph. Again, we have the blue arrows up here which control the size, so I'll just make it a little bit smaller so we can see more of the data on the screen. So we have our axes labelled in travel time in milliseconds, and along the bottom distance in meters of our spread. So you can see now that this is actually a composite record of our 3 spreads. Each spread was approximately 24 meters in length, so we have a total spread length here of 72 meters. Now, inevitably, your travel distance graph will contain some bad data points, which the first task we have to do is to edit these out. Very obvious is where we had our missing data channel, and the first thing we'll do is edit out some of these points down here. So I come to Travel Time Curve and select Delete Travel Time. I'm going to make this scale bigger again so we can see what's going on a little better. And I simply click on the travel time that I want to delete. I've probably got a bad one in here. You can see this jump, which is obviously not natural. The Earth does not behave in such a manner. And we got some bad ones at this end of the spread as well. Probably these 2 here. And we can see now that the data is starting to acquire the nature of smooth curves, which in refraction will have a dog leg on it. The dog leg is the thing that we're really interested in, because where we have a dog leg, this signifies a change in the velocity of the subsurface. So I can go and edit out our bad data points. Probably got one here as well. And so on. We can continue doing this until we're happy that we've got nice clean time distance graphs for each of our shot points. Inevitably you will get some bad data points, and it is only when you transform the data into a time distance graph like this that you can see where they are, and then you can start doing some cleanup operation, which is in essence a manual filter on your data. Of course, you have to use a little bit of care and obviously your knowledge of geophysics when doing this, because you have to remember that in any filtering process, whether it's automatic, done by the computer, or manually done by yourself, that in essence you're going to be filtering out some of the data. So be very careful. Of course, as it's digital processing, you can always go back and re-edit the data later on by rereading in from your archive the original raw data. The next thing we're going to do is a time term inversion, and we're going to assign our layer 2 arrivals. So by clicking on assign layer 2, you will notice immediately that all of our dots have turned red. What we now need to do is manually assign where the change in slope of these curves occur. So somewhere around here. So if I now click on this point here, you will see that above it all of our little red dots, which are our first arrival times, have turned green. And I need to do this for each one of the curves in turn. So I use my knowledge of geophysics to say where I think this change in slope has occurred. On some of these, it is always going to be easier with some of the curves than with other ones of the curves. You'll notice here where I had the same travel time on two different curves, it actually changed both of them green at the same time. I'm going to leave these as first layer assignments because, as you can see, the line of that curve is not parallel to these two. That means that the velocity on this line of geophones is actually higher than those. So this is probably information which relates to our first layer. When we're happy that we've read all of the information in and that we've assigned to the best of our ability all of these portions of the curves as layer 2, we can then move on to the next step and do our time term inversion. Now we can either assume that the Earth is flat, or if we had any elevation information, then we can put this information into a simple text file which we can then read in as an elevation data file. I've already done this, so I now need to locate this, which here I've called top line elevations. The software reads the data file in as being acceptable, and it now will do the inversion, and it says we've got an RMS error of 0.4 milliseconds. And here is what our data looks like when we invert it. We can see that here is the ground surface with a gentle slope across it, and we've got a two-layer case, a little bit of a dip in the middle of it here, and we have velocities of 0.5 seconds and 1.7 seconds. This shot shows the elevation file which I've created, which will add topography onto our dataset. It's a very simple ASCII file. In this case I've created it using Notepad. On the left hand column we have our geophone number on our left hand column we have our geophone location, which in this case runs from 0 down to 71 because we have 72 geophones. And then the next column simply is our elevation above a datum. In this case my datum was sea level, and I've run from 99.4 meters above sea level to 94 meters above sea level. We can call this anything we want. In this case I've called it top line elevations, SizeImage will identify this file so long as it is a simple ASCII file and in this format.